Today we are exploring Newton's second law and its application through the motion of a paper ball falling towards the surface of the Earth. In this lab, our problem is to determine whether or not Newton's second law is able to accurately predict the motion of the falling object. Based on my physical observations and the computational models, it is evident that Newton's second law is capable of accurately predicting the motion. To outline this report, I will first discuss the main physics principle used in the lab, then I will show the computational models and the video observations. Finally, I will compare these sets of data and discuss questions such as what if and what does it mean. Now, the most important physics principle used in this lab is Newton's second law. But in order to use Newton's second law, we must first use the concept of velocity, which is written here. Now, Newton's second law, which is also known as the momentum principle, is written here. A very important aspect of this law is understanding the net force. The net force is sum of the total forces. Therefore, Newton's second law cannot be correctly used unless all the forces on the system are added together. Now, we can see these two equations in the Python program here and then here as well. There are two main forces acting on the system in this experiment. The first and most obvious is the force of gravity from the Earth, and the second is the drag force encountered from air resistance. The force of gravity, which is also known as weight, can be modeled through this equation here. And then the drag force is typically written here. And so we can see that these two added together in the Python program will then compose what Fnet is. Now we can see that the drag force written here is slightly different from the way it's normally written here. And the reason for this is that we wanted to better the computational model to fit the data, so we instead took the turbulent drag force, which is proportional to the square of the speed. Now in our Python code, we had to first consider a couple of initializations. We can see the ball's mass written here. We can also see the position and the velocity vectors, which are both 0. And then we can also see the g, which is the gravitational acceleration, the j hat, and then also the proportionality constant, which we determined later from the computational model and the observed model. Now we also have to consider the parameters in the video, so we use the calibration stick to then measure the distances, and then we also had to change the final time in our computational model based on the final time in our video, which we record the final position, which is 0.367 seconds. Now initially from the model where we only have the gravitational force influencing the ball, it would seem that Newton's second law does not accurately predict the motion. And the reason for this is that the total net forces are not included because we did not include the drag force. And we can see that with the drag force included, the computational model does better predict the data. Now despite this model being better, there's still some deviation from it here. And the reason for this most likely is the visual distortion in the video. Now we can combine these two plots to create a third plot that has both the model position with the drag, without the drag, and then the observed position. And we can see that generally the model position does a good job of predicting the data. And so from this we can conclude that Newton's second law does accurately predict the motion. And we can also see that the model position without the drag tends to increase in its overprediction here. And the reason that this is because the drag increases its magnitude as the speed increases. And so as the speed increases here, the model position without the drag greater deviates. Now by asking the question, what does all this mean, we may want to consider the concept of terminal velocity. Terminal velocity is defined as when the drag force is equal to the gravitational force. From our computational model here, at the end of the time scale, we can see that this never occurs because the gravitational force arrow is always larger than the drag force arrow. Now eventually, terminal velocity could occur, but not during our short time interval. The model without drag would never be able to reach terminal velocity because there is no other force opposing the force of gravity. Therefore, the ball would just continue to accelerate downwards. Now we may ask, what if the object was initially thrown downward? Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? Using the definition of terminal velocity, the terminal velocity would not actually change. However, the ball would reach that terminal velocity faster if it was thrown downwards instead of just being dropped from rest. Now we can see that in this computational model here. Now we can see as it continues to go downward, it eventually reaches terminal velocity because the drag force arrow equals the gravitational force arrow. And we can also see that it reaches that quicker than if it was just dropped from rest. To conclude this experiment, it is evident that Newton's second law is able to accurately predict the motion of the falling object, as long as you incorporate the entire total net forces.